Mr. Chairman and all participants, I'd like to suggest to your attention the report on the topic a two-type design of metamaterial based on a quasi-fractal approach. The entry of humanity into the Internet of Things era has significantly expanded the range of tasks solved using wireless access technologies. At the same time, taking into account the mobility of users of telecommunication services, preferences given to compact solutions. Regardless of the frequency range used, the main ways to achieve miniaturization are, first of all, the use of electrically small antennas as well as the use of metamaterials. Since the elementary cells of a metamaterial in many cases have multi-component structures, the known set of approaches to the synthesis of such can be extended by passing to the 3D topology of the constituent elements. Thus, the purpose of the report is to study the electromagnetic parameters of 3D SRR structures, in which the constituent elements are modeled on the basis of quasi-fractals. Sufficiently tested and has proven itself on the positive side. The study began by analyzing two ribbon split rings without a conductor with end grooves in the outer tape. The grooves were formed using the meander fractal initiator of the first iteration, allowing for the formation of broadband zones of negative magnetic permeability. ANSYS HFSS simulator was used to study the electromagnetic properties of various metamaterial cell design, with the 3D topology designer allowing for the implementation of a configuration with 24 grooves evenly spaced around the circumference. The simulation results show many frequency ranges with negative magnetic permeability and B-negative zones with negative dielectric permittivity. The effects of various parameters of the metacell geometry on these zones was analyzed using special macros embedded in HFSS for calculating epsilon and mu values. It should be noted that in the considered version of the outer tape, the depth of the grooves was constant along the triolate. At the same time, the grooves themselves from different ends of the outer tape were arranged in a checkerboard pattern. Next, we study the influence of the variable depth of the grooves, for example, when the cuts of the rings lie in the horizontal plane and the grooves on the end surface of the outer tape are symmetrical. Efforts made to vary the design of the metacell made it possible to achieve the appearance of the DNG band in the range of 640 to 950 MHz. A variant of the horizontal arrangement of rings was also studied, which is a typical case in the formation of metalenses. At variable depth of the grooves, the DNG section shifted to the regions of 7.0 to 7.7 and 7.9 to 9.25 GHz, while a zone of negative magnetic permeability values covers a continuous region starting from about 5.3 GHz and beyond 10 GHz. The latter testifies to the prospects of using such structures for construction magnetic metalenses, for example, for electron microscopes, naturally, provided that the size of meta-rings are scaled in accordance with the given wavelength. At the end of the first stage of research, a variant of the ring structure with an external tape in the form of meander was considered. For this design, the area of negative permeability of interests in considered in the low frequency range up to about 1.4 GHz. At the second stage of the study, a combination of split rings and a stage conductor was used in the construction of metacells. The grooves in the upper strip of the metacell varied in depth according to a sinusoidal law approximating the second iteration of the quasi-fractal based off the meander. This design achieves a low frequency range with a negative permittivity and permeability from 100 to 336 MHz. The distance of the conductor from the surface of the ring did not significantly affect the width of the DNG range in the low-frequency region, since an increase in this distance from 4 to 10 mm only shift the upper limit of the range to 345.6 MHz. A more significant result regarding the influence of the late of the low-frequency zone DNG made it possible to obtain an alternative variant of changing the design of the metacell, which consists of the vertical turn of the wire and the location of the cuts of the tapes in the horizontal plane. As can be seen, the transition to the vertical wire extended the upper limit of the DNG zone in the low-frequency region to 647 MHz. At the same time, the second DNG zone was localized in the region of 4.65 to 5.15 GHz. Summarizing the results of the second stage, we can draw intermediate conclusions. In particular, in order for the DNG zone to be in the lower frequency region, it is necessary to place the cut in the outer tape at the top of the z-axis or in the horizontal plane. The location of the cut in the outer ring on the z-axis from below leads to the disappearance of DNG in the low frequency region. To study the impact of deviation angles of conductor orientation, a limiting case of 45-degree deviation was considered. The result was a narrowing of the B-negative zone to 340 MHz, primarily due to ring rotation to align slots with the vertical axis. Thus, to maximize the expansion of the lower DNG strip, cuts in the ribbons must be in a horizontal plane. The deviation of the conductor from the vertical at an angle of up to 45 degrees does not affect significantly. The next stage of the research consisted of the translation to a conductor located perpendicular to the plane of the rings. At the same time, the grooves in the upper cut tape at both ends had a variable depth and were located in a synchronous manner, that is, the grooves from opposite ends were opposite each other. An important nuance was also that the sections of the tapes lay in a horizontal plane. As a result of this modification of the metacell design, there was a significant expansion of the DNG bandwidth and lower frequencies, ranging from 25.02 MHz to about 652 MHz. This corresponds to 185.22%, then converted to a relative frequency value according to the factorial bandwidth formula. There are also DNG bands in the ranges from 3.25 to 3.7 GHz and from 4.1 to 5.05 GHz. Another of these zones is in the range of 8.25 to 8.75 GHz. Thus, the turn of the conductor perpendicular to the plane of the ring's top design in an effective solution that led to the expansion of the bandwidth in the corresponding DNG bands. As expected, with the vertical arrangement of the conductor and the horizontal arrangement of the ring in the XY plane, the DNG band disappears in the low frequency region. However, in this case, if the conductor is placed horizontally, parallel to the plane of the rings as shown in slide, then the specified low frequency section is restored. At the same time, its width becomes relatively smaller, 1 to 0.44 GHz. At the same time, the DNG bandwidth in the region of 7.05 to 7.75 GHz is 700 MHz. If, however, the conductor is placed in the intra-annual space, then regardless of its orientation relative to the cuts in the rings, the low frequency range of the DNG disappears. In the final stage of research, the metacell design with a conductor perpendicular to the plane of the ring and with cuts in the tips located on the vertical axis was considered. When the cuts are on the z-axis with the same width as a conductor, the low-frequency DNG region disappears, but is preserved in the region of 4.8 to 6.35 GHz. The deviation of the cut in the upper ring from the z-axis in this case leads to the restoration and expansion of the band of the low-frequency section of the DNG as the cuts deviate from the vertical position. The maximum strip in this design option is achieved when the cuts are located in a horizontal plane deviation 90 degrees from the z-axis. At the same time, the presence of a low-frequency DNG section at 45 and 90 degree angles of the cut from the z-axis depends on the width of the cut in the ring. Future research should focus on expanding the low-frequency range and obtaining more broadband DNG solution across the spectrum. These could involve using a sequence of grooves in the inner tape and exploring the use of other geometric figures as indicators of quasi-fractals, as well as studying the influence of dielectric fields. Additionally, research will investigate preserving the properties of a single cell in a multi-cell metamaterial, considering both relative position and multi-orientation of the metacells in a space. The best solution for achieving negative dielectric permittivity and magnetic permeability was found to be using a conductor perpendicular to the plane of the rings with synchronous variable deep grooves on both ends of the outer tape. The use of a two-ribbon structure as a basis of a metamaterial cell provides a wider relative frequency band compared to using them as an antenna. The indicator of the relative frequency band of the DNG zone achieved in this case was 185.22%. In previous works, this value does not exceed 132%. It is concluding of my briefing. Thank you for your attention.